If you've used an HPC system provided for you by a central facility or by your company, chances are that somebody very clever figured out lots of things to make sure life is pleasant for you and your code, so it has a best shot at running fast. Now, obviously, big things matter, like which CPU you choose or how your Lustre file system is configured. These will all have a big impact. But there's also dozens of little things that matter too. And if they're not done, they're paper cuts, hurting your performance, but not quite drawing enough blood to be fatal. Now, today we're going to talk about some of the little things that we build into ParallelCluster that make a big difference. This is just scratching the surface, though. ParallelCluster has been around for quite some time now, and it's packed with little nuggets that just keep the lights on without you noticing. Stephen Sachs, one of our resident performance nerds, walks us through some of these. And if there's something you think we should be building in a ParallelCluster, don't be shy. Reach out and let us know. And while you're there, don't forget to subscribe to the channel so we can keep you up to date on all things related to HPC at AWS. Let's get to it.
So let's start with the first and I think the most obvious one for everyone who's ever run a Fortran code. Like, for example, Wharf is a good example of that. If you just run that on a new Linux box and you run it at a certain size, you will just hit a wall. It would just tell you segmentation fault, no further explanation. Code died because it couldn't write to where it wanted to write to. After digging through this a lot and probably Googling it, you will find out that the problem is most likely the stack size. There is a thing called the ulimit, like how much is the user actually allowed to use, and that is set by the operating system, usually to some sane values for everyday Linux use. But of course, running a 60-year-old Fortran code on the biggest box that you can find is usually not the typical use case you would see for a Linux box. So that's why those things don't work by default.
So ulimit gives you access to all of these slightly arcane under the hood settings.
It's like the Linux housekeeping tools. There's nothing particular about this. It's just that these are the kind of settings you have to know when setting on an HPC system, and that's one of the things that we do for you. So if you look at stack size, here it is, 8192 exactly. Another one you run into a lot is number of files. So those are the things where we have, and a couple of those others where we have just increased the limit to make users not fall into that trap. If you look at the file system setup, of course, there's a whole lot you can do on ParallelCluster. I'm logging into the head node here. So this, if I do a show mount -e, it says, what does it actually provide as a mount to other instances? So these are all the instances, these are all the file systems that are actually mounted by the
compute nodes.
The compute nodes, exactly. So in this case, my home and my shared are actually an NFS share coming from the head node. That's not always the case. You can configure this to be FSX or EFS or whatever you want it to be. Yep. But there are some like /op/slurm or /op/intel. Those are always going to be an NFS mount here. So NFS is a great technology because it's really easy to set up to just share file systems across Linux boxes.
But
again, there's the scalability issue. I mean, so if you have if you share this with 5, 10, 20 other nodes, and every once in a while they read a file, that's all fine, that's all good. But now imagine you have something like you do an MPI run here. You boot up a couple of instances. Let's say you boot up 100 instances, each with 192 cores. And then you say MPI run, and you want to use the Intel MPI run. that's going to go to /opt/intel and look for a couple of libraries there. And probably every one of those 192 times 100 are going to do that at the same time. So that's not exactly the use case NFS was initially made for. So that's
back
why
in 1983 or whenever it was that NFS was created.
But they have mechanisms for that. I mean, it's so what they can do is they can multi-thread the NFS server, and that's one of the things we do here as well. See, there they are, 256 because this is a big box, and then 1 for the grep.
So we scale the number of NFS threads, NFSD threads that we run on the head node with the size of the head node, right?
Exactly. Yeah. So that if you, for example, decide to have a tiny head node, which in some use cases that's really a good thing to do, that's not going to be overwhelmed by NFS threads and just running out of resources.
Right. But it also means that this is also another sort of performance hint towards customers. If you need extra performance out of a head node because you've got a really large, like numerically large number of compute nodes you're anticipating spinning up, it'd be a good idea to scale up the size of your head node.
I think
and you
that's
get
one
sort of a bunch of optimizations for free when you do that. So this is the page where this is the changelog for ParallelCluster. This is a really good place to go text searching if you want to see if we've made a particular change. So, for example, if you wanted to find whether we'd done something to your limits at some point in the past, this is a good place to go looking. And in fact, you can hop around and you can see that quite some time ago, we raised the number of open files to 10,000. This is quite a long time ago because this was in ParallelCluster 2.4. But you can track some of these changes that we've done to ParallelCluster through the ages by just sort of sifting through this monster file.
So there's something called like the C states, which means, and I always find this hard to remember, the lower the C state, the higher the frequency. It's like kind of like that. So C0 would actually be the processor is firing at full speed and it's going ahead and there's full load on it. And then there's C1, which is actually, okay, there's no load on the processor right now. And then there are the higher C state, the higher numbers, which are actually where the processor goes into a sleep. So there are good use cases for this. The obvious one, of course, is if you have a laptop or anything like that it just saves power. In HPC, usually that's not what you want. It comes with a cost of re-enabling the CPU. So when the CPU gets low again and should do something again, it needs some time to wake up. So what we did here, we're actually limiting in ParallelCluster the C state just to go between 0 and 1.
And so we're doing that on the kernel command line when we boot an instance.
Exactly. This is a kernel parameter, so this is baked into the AMI, and this happens when you boot the instance. Okay. So there's another one of those typical things that you would see on a compute node, and that is like bringing down the operating system noise, bringing down what the OS does, what you don't want to interfere with your performance.
Like every 10 minutes, checking cron.
So there's exactly cron is one of those is one of those jobs, and by default there's a couple of householding things that Linux will do in those cron jobs, and we just don't want them, so we turn them off.
If you're enjoying these videos, please give us a like and consider subscribing to the channel so that we can keep making more to help you understand how the cloud works and to show you new ways to help all the scientists and engineers around you who use HPC every day to do amazing things. It's what gets us motivated as well. See you next time.